Hi all, this is Vishal Singhal from Self-Start, your host for today. So today we have Ms. Kanupriya Bhargava, statistician from Royal Society, and she is taking us through generalized linear models. So I'll just uh, hand over the presentation to her. Kanupriya, you are ready?
Yes, I'm ready.
Right.
Right. So I'm hoping my screen is visible now.
Yeah.
Okay, great. Right. Hello, everyone. Thank you for joining. Before we begin, let me just quickly introduce myself. I'm Kanupriya. I work as a data science consultant. I have a master's degree in financial statistics and a bachelor's degree in mathematics. I'm also a member of the Royal Statistical Society and have a graduate statistician accreditation from them. So the topic of this webinar is generalized linear models. These models are heavily used in insurance and credit lending. These can be thought of as an extension to linear regression, where you can model different types of response variable. These can include both discrete and continuous variables. So what exactly are generalized linear models or GLMs? Just a little note here. From this point onwards, I will be using the abbreviation GLM for generalized linear models. Right, so what are GLMs? They are regression models. That is a model relating a response variable y to a vector of explanatory variables x. In linear regression, y is continuous. So when it comes to modeling discrete variables, for example, linear regression is not the correct choice. What GLMs essentially give us is a way of modeling discrete and duration variables in addition to continuous variables. So, which is why there's a need for generalized linear models that can handle variables uh, which give discrete values, duration values, and of course GLMs also incorporate continuous variables. So before we delve into the details of GLM, let us look at a summary of how different types of responses and what models can be used for modeling them. So first, for modeling continuous variables, of course, we use linear regression heavily. For example, we would use linear regression when we want to model the height of a group of people based on their weight. So height is a continuous variable, which is why linear regression works fine in this case. Now, for the next category is nominal variables, binary, which is they have two responses. Uh, say whether someone we want to model whether someone will default on a loan, where the response is 1 if they default and 0 if they don't. So in this scenario, we use logistic regression. Third, nominal with more than two categories. So this is similar to the idea is similar to the binomial response variable, but we have multiple categories. For example, we want to model which product out of n different products a customer will buy, where n can be anything greater than 2. So we label different products as 1, 2, 3, etc. So of course the order does not matter. So we have n products. We can label them from 1 to n. We can even switch. So say product 1. In one case, product 1 could be labeled product n. In another case, product 1 is labeled product 1. So here we use the multinomial logic model. Number 4, ordinal variable. Now, ordinal implies that there is an order to the response variable. For example, we want to model the grades of a class of students. Now, suppose that the only possible grades are A, B, and C. We can label these as 1, 2, and 3 respectively. So now obviously 1, which is A, has a higher rank than 2, which is B, which has a higher rank 3, which is C. Now I could also label A as 3, B as 2, and C as 1. You can label them in any way as long as the order is preserved. And for this type of a problem, we can use the cumulative logic model. Examples for count data uh, include, say, you want to model the number of employees in an organization, the number of claims insurance company receives in a certain period of time. Here we use the Poisson regression when x includes continuous variables, and we use the log linear model if the vector of explanatory variables x contains all categorical variables. Now, sixth is duration. And duration, as the name suggests, is the duration to an event. For example, we're trying to model when a customer will churn. That is when they will end their association with a business. The event here
Oh,
is the customer churning.
so question here was what is the duration variable? Is this how we would define duration here? Duration variable?
Yes, yes. So um, just bear with me for another
Uh,
few seconds. I'll
uh,
explain. So yeah, so it's the variable is the duration to an event, right? So if we want to model, like I was saying, so if you want to model when a customer will churn, that is, so the event here is when the customer ends their association with the business, right? So from the point where they become a customer to the point where they end their relationship with the business is the duration. So now that is our variable, right? I hope that answers the question. Right, so as we only have an hour, I won't be able to cover all the different models. So I will discuss the key concepts of GLMs that can be applied to all the models, and then I will go into details for some of the models. So GLM has three components. The first component refers to the probability distribution of the response variable. For example, normal distribution for y in linear regression. Now, for each observation I, we have the expected value mu I as per the distribution. Again. Yeah, so you have the variable yi and you have the expected value yi is equal to mu I for each observation I. Then next is the systematic component. We have a linear predictor, which is a linear combination of the predictor variables. Right? Please note that this is different from our response variable. It will become clear in the next few slides when when I list out some examples. The third component is something called the link function, which defines the link between the response variable yi and the linear predictor, this expression over here. In other words, it explains how the expected value of the response variable, this value, is related with the linear predictor of the explanatory variables. So I'm just going to pause here for a second if there are any questions.
And go ahead.
Okay. So first, we start with a simple case of the GLM, that is the linear regression. The model form is simple. Y is equal to beta naught plus beta 1 x1 and so on for all p predictors. Right. So now let us look at what the components of the linear regression model are. So first is the random component, which describes the distribution. Here, y is normally distributed, and as some of you may be familiar with the linear regression assumption, the error term is normally distributed with mean 0. Next is the systematic component. The linear predictor here is quite straightforward. It is just the linear combination of the explanatory variables as in the expression here. Right? The link function here is just the identity function. That is g of mu. Right? G of mu is just equal to mu I, which is equal to the linear predictor here. This is our expression for the linear predictor. Right. So let us look at an example for the linear regression. So we look at a simple example of the linear regression. Suppose we want to model sales. We have two predictor variables, TV and radio. TV is the advertising spend on television, and radio is the advertising spend on radio. And based on the advertising spend on two of these different media, what we want to do is model the sales. So essentially what we want to do is regress sales on the variables TV and radio. So here's a snapshot of what the data looks like. So what we have here is sales in thousands. Then we have the first observation as 22.1 thousand. Then spending on TV as 230.1 and then 37.8, and then so on for 200 observations. Now, what we want to do in the model is basically using this sales as our y variable. We'll build a linear regression model. So we run a regression model and we get these results. Right. So the coefficient for TV is 2.92110, and the coefficient for TV is 0.04575, and for radio is 0.18799. The p-value for both of these is less than the usual threshold of 0.05. Hence, both these variables are significant. Now let us look at how we would interpret these coefficients. So if we were to increase the TV expenditure by 1,000, the sales would increase by 46 units on an average. And similarly for radio spend, if we were to increase that by 1,000, the sales would increase by approximately 188 units on an average. So the interpretation, building linear regression and interpretation for linear regression model is quite straightforward. It gets slightly tricky when we go to logistic regression and further models. So next we look at logistic regression, which is mainly used for two-class classification. This model shows how a binary response variable depends on p explanatory variables. So looking at the components, the first component, the random component, we assume that the variable y follows a Bernoulli distribution. The Bernoulli distribution is where the random variable can take two values, say 0 and 1. 1 would denote the probability of success, which is pi, and thus the expected value of y is pi. This expression over here. So in logistic regression, essentially what we're doing is we're modeling a probability. The systematic component is the same as before, this expression over here. Now the link function g of mu. So this is now the logistic function. Mu is, so if go back to the specification. Yeah, so mu is just the expected value of yi, right? So what we have, expected value of yi is this probability pi. So mu is equal to pi I. So this is the form of the link function, right? So we want the link function in terms of the response variable, which is this pi. So what we have here is mu is equal to pi I. So we have g of mu equal to g of pi. And in terms of pi, we have this expression, natural log of pi divided by 1 plus pi. So why this form? This form ensures that we get a response variable between 0 and 1. And of course, since we're modeling a probability, we need this value to be between 0 and 1. Because obviously, one probability cannot be greater than 1 or cannot be less than 0. So we need to ensure that what we're modeling, which is the probability, we always get a number which is between 0 and 1. So this form of the equation, this link function, implies that the probability is given by this expression, which is e to the power the systematic component, the linear predictor, divided by 1 plus e to the power the systematic component linear or the linear predictor. So looking at an example of the logistic regression, apologies, I should say logistic regression. So what we want to model is default of credit cards based on the bank balance. So when somebody defaults, our variable y would take the value 1 and 0 if they don't default, right? So here's a snapshot of the data. We have the default, whether or not the person defaults is going to be yes, no. Then because we've assumed that when it is default, it's 1, and then when there's no default, it's 0. So what we'll do is encode this variable. So no is 0 and yes is 1, right? And then we have the bank balance. So, and a total of 400 observations. So next, what we want to do is run a logistic regression using this data, and we get the following results. So this is the model output. So we have the intercept and coefficient for the variable balance, since we only use the one variable. So the slope for balance is 0.0055, and the p-value is again less than the threshold value. So this variable is significant. So now the question is, how do we use this coefficient to number one, model the probability of default, and second, once we have the probability, how do we classify it? Like so the response variable is 0 or 1. So when we get the probability, how are we doing this classification of 0 and 1? So let's look at the equation for this form again. So this is the probability by I, right? And the equation for that is this e to the power beta naught plus beta 1 into the variable value and so on, divided by 1 plus this value again. So using this equation and our model results, we'll first estimate this probability. So, so suppose there's somebody that has an average balance of 1,000. Now we want to know what is the probability based on this model that we built that this person will default. So all we need to do is plug in these values into this equation. So we have the intercept, then the coefficient for balance, and then balance. And since we have only one variable, so ignore the rest of the terms. So we'll only use till 1 here. So plugging these numbers into the equation. So you have your intercept, slope, and then your value of the variable, which here we assume is 1,000. So this is 1,000. So the probability of default is 0.006. Now the next scenario. So here the balance that the person had was 1,000. What if the balance was 2,000? So similarly, plug the numbers into the equation, and then you get this value 0.586. So now we have the probabilities, but how is the logistic regression giving us that number of 0 and 1? So this is what we do, which is we set a threshold for the probability. And now if the probability that we get is less than the threshold, y is equal to 0 and 1 otherwise. So say suppose you're using a threshold of 0.5. So if the probability is less than 0.5, you say that y is equal to 0, which is this person will not default. And the probability of greater than 0.5, y will be equal to 1. So you'll say that this person is likely to default. So this probability threshold can be changed. So suppose you can change it to 0.6 or change it to 0.5. So only when the probability of defaulting is really high will you classify that person as a defaulter. Right, so moving on to the Poisson regression. So this is used to model count data, where, for example, like I described earlier, you're trying to count the number of employees in an organization, or this this model is heavily used in the insurance industry, where uh, they usually want to model the number of claims coming in a certain period of time. So the outcome variable is a count, and the components of this model are as follows. So you have the random component y, which is the response variable, and y follows the Poisson distribution. The Poisson distribution is essentially modeling the number of events that happen in a certain period of time. So, so suppose you were trying to model like what the number of cars that come into the drive-through in a 15-minute period. So that count follows a Poisson distribution. So, and this is Poisson distribution is defined with the parameter for that is this mean value. And so you have the expected value of y is equal to mu. And the systematic component, again, is the same as before in this case, which is the linear combination of our predictor variables. So the link function now is defined by this value over here, which is log of mu I. So, so what you have is log of mu I is equal to this value. So when you want to, if you want to know what the value of mu is, all you have to do is take the exponential of this expression. So looking at an example of this. Okay, right, apologies. Ignore the first line. I'll just explain what the data is. So, so this is quite an interesting data set, which I saw on the Penn State Statistics website. So it's on the species of crab called horseshoe crabs. So where the female has a certain number of males always all surrounding it, and those are called satellites. So they are smaller in size, and so in essentially like how a satellite works, always around a big object. So this is how the horseshoe crabs uh, also follow the female. And so this was quite interesting problem where they were trying, where we want to model the number of these satellites around the horseshoe crab based on the width of their shell. So you have the count of satellites, and then you'll have the width of their shell. So again, using so we use a Poisson regression to model this, and this is what our results give us. So you have the width coefficient as 0.1640. And again, the p-value is less than 0.05, which means that this is significant. So the interpretation for this is not straightforward, right? So once you plug this back into the equation, you'll get the estimate for the count, but the interpretation is slightly tricky. So now, of course, since beta is greater than 0, which means the wider the female crab is, the greater the expected number of male satellites are around it, right? So this is the coefficient, right, which gives us an order of this. So what this number means is essentially that if one were to increase the width by 1 unit, the number of satellites will increase, since obviously this number is greater than 0, and that count will be increased by a factor of 1.18. Right. So yeah, that is all. That is all the models I have for today. I hope I haven't rushed through it. So I think it's a good point to take any questions now.
Kanupriya?
Hello.
Yeah, you were not audible for something. So there is a question here. Could you
Yes.
briefly explain P, T, and Z values?
Sure. So right. So well, so mathematically, the t-statistic is the coefficient divided by the standard error, right? So, so you have this divided by the standard error, you get the t-statistic. So why we use the t-statistic is we want to see whether or not the variable is significant. So if the coefficient, so this value, coefficient divided by the standard error, follows the t-distribution, which is a bell-shaped curve, which is very similar to the which is very close to the normal distribution. This t-distribution has a mean 0. So what we're doing is we see this t-statistic, which we get using this value, this divided by this, where on the distribution it falls. So if it falls on the very extreme end of the distribution, which means the probability of this getting this t-statistic by a random chance is very low, which means that the coefficient that we got for this particular variable is significant. So this is where the p-value comes in. So this is the probability of this t-statistic, the probability of this t-statistic being this value or more extreme values. So since this probability is very low, which means that this t-statistic we did not get this by chance, right? So which would mean that these coefficients are significant, and in extension that a variable is significant. The Z statistic is also exactly similar. Only thing is because of the form of the model, this value standard, this coefficient divided by standard error now follows a Z statistic. So this follows a it's essentially a z-score which follows a normal distribution. So the idea is the same. Again, if this statistic falls on a very extreme end of the distribution, which means that the probability of getting another value similar to this, close to this, by randomness is very low. So we conclude that, again, this variable is significant. Right. Any other questions?
No other questions.
Okay, well,
Go ahead, no other questions.
yeah, well, I have reached the end of where I was. So yeah, so this is all I had for today. So I'll just wait for another minute for any further questions.
Would you be able to share your contact details just in case people want to connect with you?
Sure. So what I'll do is after the end of the session, I can post my LinkedIn contact on the I think you can post the message on there, right? In the webinar page, the event page.
Sure, you can. Okay. I've sent you a question. Please go through that.
Right. So no other questions at this point.
So I have sent you a question. Can you please check that? In case of T distribution, it's a normal distribution. How about in case of Z?
Right. So T distribution is different from the normal distribution. Right. So when we calculate the standard error and the coefficient, so based on the model, these will follow different distributions. right? So the t-distribution is similar to the normal distribution in terms of its shape, and when the degrees, so this variable, this component of the t-distribution, the degrees of freedom, when it exceeds the number 30, then the t-distribution is very close to the normal distribution, right? So and the z statistic is essentially calculating the z-score, right? So what we're doing is you have the mean and you have the standard deviation, or an estimate of the standard deviation, which here is the standard error, right? So this z statistic uh, essentially represents how many standard deviations above or below the mean population that number is, right? So again, when you so this again follows a distribution very close to the normal distribution, and then when it goes when you take many such examples, it gets very close to the normal distribution, right? So in terms of the shape, both t-distribution and the z-score, which is essentially what you're calculating, is the so once you calculate the z-score, that is essentially the normally distributed variable. But yeah, so these two are different, but in some sense, the idea is that they also follow a bell-shaped curve where towards at the tails you have less probability of the variable occurring, and then you have more probability of the variable occurring in the center, and they're symmetrical. They're both symmetrical around the mean.
Another question is it true that the data has to be normally distributed before applying GLM?
So, so that's essentially why we're using GLM. So assuming that everything is normally distributed does not always work, right? So you can have different distributions. So based on the distribution that your variable follows, you can use different types of GLMs. So in logistic regression, we said that the variable follows a Bernoulli distribution. And in Poisson regression, we said that our variable follows a Poisson distribution. So, but when it comes to linear regression, the assumption is that y follows a normal distribution. So when you're actually doing a linear regression and then you're checking whether your y follows a normal distribution or not, it's not a necessary condition that you can only apply a linear regression only if you take your data, build a histogram, and you see it's following a normal distribution. The way the assumption is satisfied when we say that we're modeling y when we're regressing y on x, and we're assuming that the errors are normally distributed. This is sort of a heavy mathematical proof, but y given x, that is what follows a normal distribution. So it's not something you really have to worry about, but you do have to check how different your error terms are once you build the model, how different the error terms are from the normal distributions. If they are very different, then you may need to do some transformations, etc. But making sure that your y itself is normally distributed is not required.
Okay. Another one is what if we cannot make it normally distributed even after applying any functions? What is the solution? Would the GLM still work?
So it will work and then will give you some results, that's for sure. But only thing is that if you make, so the assumption, if the assumptions of the linear models are not satisfied, then it's probably because what you're trying, you're modeling it as a linear regression, but the true underlying relationship may not follow a linear regression. So of course you can do, there's different things you can do, transformations, um, you can do log transformations, you can do box-Cox transformations, etc. That's something you can try, but if still it doesn't work, then probably linear regression is not the best approach. Then you should maybe look for other approaches. Maybe perhaps that the relationship is not linear at all. So using a generalized model is not the correct solution.
So theoretically, we can write our own link functions and apply regression.
Well, so there's standard models that in terms of GLM that that we use, but so essentially this is what you're doing, is you're doing a transformation on the variable y. So there are a few standardized transformations that you use, but if you want to get really creative and try your own transformation in the variable, right? So that could work. Not sure if that really depends on what your thought process is behind making a transformation on that variable. So as long as there's some logic behind it, you could try it, but it won't be a GLM model in theory. I mean, theoretically, it won't be a GLM model, but then of course, lots of times you have to try on different transformations of the variable. That's to see if it works in linear regression. And also if you, so in the GLMs, you have a standardized sort of interpretation of these, right? So if you make some sort of a link function and then you try to interpret it, it might be that, it's too complex, or it's not quite interpretable. So depends on what you're after.
Okay, one last question. Can you briefly explain the degree of freedom?
Right. So the
Gentleman
degree
was
of
gentleman was hesitant in asking it. It may be a 2 mark exam question.
yeah. So uh, the degree of freedom is somewhat so in intuitively, degree of freedom is um, like how many free variables you have to make that estimate, right? So when we're talking about the t distribution, you have a linear regression, right? So you have n observations and you have p predictors. So in that case, your degree of freedom is n minus p minus 1. Minus 1 because you also have the intercept in addition to the p predictors. So this is in terms of the t statistic, but degree of freedom varies depending, as in how the exact number of the degrees of freedom depends on what your context is. But essentially, you can think of it as, say, how many free variables you have to make the estimate. So in linear regression, for example, you have n observations, which is, say you had n points, right? But then now you've estimated p you have p coefficients which you've estimated using those endpoints, and you have also the intercept, which is 1. So n minus p minus 1 is essentially a count of how many free variables you have.
Okay, one last question has come in. So if GLM is not applicable, what are the alternative models or solutions that are?
Right. So GLM is used when you assume that this is that you have a linear relationship, right? So say I was modeling add a time series. So then I'll use time series techniques. Or if uh, if I don't see a linear relationship, so I can try something that doesn't confine my model form to a linear form. So I could try tree-based methods. For example, I could try more machine learning techniques like SVM, etc. So yeah, so in machine learning, there's quite a few techniques where there's no it does not place sort of constraint on the model form that it has to be linear. So tree-based methods are quite good in that sense, because you won't have a model form to actually begin with. So my choice would be a tree-based method, but then there's lots of machine learning methods out there which you could use.
Great. Thank you for answering all the questions. Any other questions, audience? We still have 10 minutes to go, but I think no more questions are coming. Any final questions you have in mind? So I have posted that this session is being recorded and will be available live on our YouTube in 2-3 days time. So Kanupriya, a lot of people are saying great session, nice explanations.
Right, thank you everyone, and thank you for attending. Hope
So
you
thank
found
you
it
all.
helpful.
Yeah, thank you all for attending and have a great day ahead. Thanks, Kanupriya.
Thank you. Bye bye.